Okay. How's everyone doing? Okay, good. On Tuesday? Yeah, so on Tuesday, I was in New Orleans. Yeah, so we have a convention with mechanical engineers, usually around this time of the year. It's a little earlier, and so I wasn't able to be here. I hope, though, that you were able to use the time to work together, to watch the videos, to ask the TA question. I actually didn't get any questions about anything after that, besides the common attendance ones, which I get quite a few of. So the last session was session 16 on combined loading. And that's where things start to get a little bit interesting, right? Because you're thinking about how stresses and how normal stresses, how shear stresses, right? They are acting at the same time at the same location, okay? And then if you even change the orientation, right? We move to a different part of the body, we see that there's a different state of stress. So it's a very exciting time. Today, what we're going to talk about is how at a single location we can get what appears to be a different state of stress. Okay? So remember when we were talking about tensile testing and we're like, hey, this is a normal stress. Okay? And it's normal in this component all the way through. But if we rotate by some amount, now what we're going to say is, hey, there's actually a different state. It's not always just thinking about it as just a normal stress. I have a normal stress. Okay, I think it'll become more apparent as we do this. Okay, so today we are on session 17. Okay, and this is on plane stress. So we're talking about situations where the material can be thought of as being pretty thin, okay? So the situations we've talked about with pressure vessels, right? Those are typically pretty thin walled, okay? But we're going to apply the ideas of plane stress, okay, to things or objects that are not thin as well, okay? And what we'll be showing is that the orientation of your element matters, again, okay? But before we do this, I wanted to kind of cover just a couple basic ideas, all right? One, let us say that I've got an area, okay? Well, actually, yeah, let's not even say that yet. We'll just say that this is some A, little a, okay? And this is a right angle triangle, and this is theta, okay? If I want to know the lengths of the side of this triangle, right? What's the length on the adjacent side? Yeah, it's just A cosine theta, right? And on the opposite side? B sine theta, right? Okay. I haven't really started off this basic before, but I think that maybe it will be helpful for what we're going to do in a few minutes, okay? Now, if I were to say that this were somehow a structure that had some area to it, right? Like this, kind of, okay? Like this. and this were some big A, okay, assuming, right, the structure is the same depth, right, you know, it's not like doing something crazy, what would be the area of this side? Okay, assuming that this length and this length, right, and the length back there, they're all the same. What would be the area on that side? It's not a trick question. The same, right? It's big A here, right? And this side is going to be big A. Right? On that side as well. Okay. So when we think about cutting elements in a few minutes, we're going to use this principle. The other principle we're going to use, all right, is kind of maybe even more basic. Here's a force vector. Okay, a force vector. And if I divide it into its horizontal and vertical components, this is going to be f cosine theta, and this is going to be f sine theta. And of course, when we do this, we want to be very careful that we go from here to here, and then from there to there. And keeping these arrows in mind, right, will help us know if we're adding vectors, you know, the horizontal components are adding to each other, or the vertical components are adding to each other, right? So, now, what does this have to do with transformations of stress? Let us say that what we have is a nice little element of stress. And this element is undergoing some sigma x. Okay, where this means that this is the x direction and this is the y direction. So you think this element is just under normal axial stress, sigma x. Okay, but what if we want to look at an element at the same location? So this is on some part of a component, same location, and let's say that's at big A. Actually, let's use a different letter. Let's say it's at some big, I don't know, Z? Okay, fine. Well, Z, that's an interesting choice. Let's just say it's at some big E. We're not going to use E today. All right. So it's right there. Now I draw another element that is at a different orientation. Okay. Like this, let's say. And what we typically do is we say that this new element is going to be having an x prime direction and a y prime direction, just like this. Yes?
So essentially it's the same, you're just rotating the selection.
That's right.
Okay.
So the rectangle, the material element really is infinitesimally small.
Right.
Okay? Okay, but it has some delta length, some delta height, or some delta width, some delta height, right? And all we're doing is we're rotating this element, but it's at the same location, right? So rotated element at same location E. So what does this mean for the state of stress? Well, maybe a simpler case would be to rotate 90 degrees, right? If we rotate 90 degrees, okay, so if we rotate 90 degrees, and we'll say counterclockwise, okay, then what we've got is a new element. Let's see, different color. Okay, what's coming out of the top now? If I've rotated 90 degrees counterclockwise, you guys tell me what's coming out of the top. Huh? Okay, good suggestion. So you're thinking sigma x would be coming out of the top. I just want coordinate system first. Yeah, okay, we'll call x prime, okay, following our convention. Okay, so we have a little coordinate system, x prime. Okay, now
45 degrees or
90 degrees. We rotated 90 degrees. We rotated 90 degrees, right? So we said this box, is right on top of this one. Okay, so x went to x prime, okay? And y is going to be going to y prime, so y prime is now coming out that way. Okay, can everyone see this? I can still write, I'm okay still writing that this is x and this is y, in fact. I'm okay with that. But I've rotated the element 90 degrees, and now I have a new x prime and a new y prime. The state of stress, okay, or the direction of the stressing arrows, shall we say, okay, or the vectors of stress, okay, those have not changed in this case. So the stress, okay, is still, this is still sigma x, like that, okay, still sigma x. But now, if I want to write it in terms of the new frame, okay, the new rotated frame, what I'm going to be looking at is, what are my sigma x prime? What is my sigma y prime? And what is my tau x prime y prime? Okay? So you tell me, in this case, we'll get to the combined work section in a little bit, guys. Folks upstairs, I'm glad you're working together. I really am, okay? Just let's keep it down so we can do this part, so then it facilitates the next part, okay? So, what is sigma x prime in this situation, in the rotated state? Good, which is? For this situation, right? What was it here? Nothing was coming out in the y direction, right? So it's just 0. Okay? So this is going to be 0. Right? I think you know where this is going. What is sigma y prime?
sigma x.
Sigma x, which was sigma x, right? Notice something interesting here. Sigma x did not become negative in this case, right? Sigma x is still coming out positive relative to the y prime. Okay, so it did not change its sign. Tau x prime y prime, that's going to just be 0 again, right? Good. So that's like the basic case. Now let's talk about what happens when it's not a 90-degree rotation. Okay. What is the key to success in this class besides continuity, and geometric compatibility. What is the big key, right? You have the big three. Geometric compatibility, continuity, right, or constitutive equations, or, you know, material deformation. The big thing is equilibrium, right? So we got to think equilibrium. And there are going to be shortcuts you can take later, which I will want you to do, okay? But for now, what we want to talk about is understanding how these transformations actually are working with equilibrium in place. So, for this, what we're going to do is we say, okay, our original configuration was this, okay? And we have some x, some y, all right? Our new configuration, okay, let's do it not at 45, let's do it maybe like, I don't know what this is, maybe 30, something like this, okay? Wow, that's really crumb de lion. Okay, so what we actually do here is we define the rotation, okay, coming, I want to use, let's do this way. We'll say that's dotted along with the x, and then coming out of this face, this is going to be the x prime. Okay, and then of course, coming out of this face, that's going to be the y prime. Okay, and the angle of rotation is going to be theta. Okay, and you can watch the videos, we go through this in detail. But sometimes it's nice to see it in slow-mo, or slower-mo, or live, however you want to look at it. Okay, so here we've got a rotated element. What in the world are we going to do? How are we going to make these two things equal to each other? What do? A twisted form of method of sections. We start with our square, our lovely square. Okay? And then we take a slice. Let's make it like that. Okay? We take a slice. And I'm actually going to move that slice over to a nicer area, a nicer region, where it goes through this upper left corner. Okay? Now, this is where it's very useful to exaggerate. Okay? If I were exaggerating properly, and I said this was less than 45 degrees. Okay, if I said, so we're going to say, let's say that sigma and theta in this case, theta less than 45 degrees. Which of these angles, this is a right angled triangle, which of these is less than 45 degrees? The upper or this bottom or this right one? The top left one, right? So when you take the slice, this becomes theta. All right, so if you had a small rotation here, right, then what we're saying is that you've got this nice kind of little sliver slice, okay, where theta is pretty small. So what do? Now we come over here and we draw another triangle. And again, I'm making it exaggerated. Even more exaggerated, like this. And this is the theta. Okay? I didn't draw any states of stress yet. So there's nothing. This is all in equilibrium at zeros. Okay? We're just talking about the method of sections. Now, let's think about the stresses that could be here involved, okay? What could be involved? In this original format, we could have sigma x We could have sigma y. And we could have tau xy like this. Okay? So now we've gone and made it more complicated. Where are these stresses in this scenario? Well, we can say that we have a tau xy, okay, acting on that face. All right. We have a sigma x acting on that face. We have a sigma y acting on this face, and we have tau xy as well acting on that face. Okay. So what's the point of this? What's the point? Well, guess what? Now, this face, remember it's exaggerated, what's coming out of this face? What's normal to this face?
X prime.
Yeah, x prime, right? So we've got prime time coming out, right? And we've got something moving along this face too. Look at it. We've got a tau x. That's right. Okay? Okay? So now we've got stresses acting on a triangle. How would you go about doing equilibrium here? How would you equate the purple stresses and the orange stresses? What?
Pythagorean theorem.
Okay, Pythagorean theorem. Okay. That will tell you something about the lengths.
I mean, the length of a vector is like maximum, right?
Yes, okay, and yes, go on.
Coordinate transformation.
Coordinate transformation, yes, that's what we're doing, yes, exactly. Okay, geometrically and with your force vectors. Okay. Actually, sorry, it was Junie, right? I got your name wrong. Oh, I did get it right the first time. Where's Junie? There you are. Okay, sorry. Go on, Junie. Okay, thank you. Okay, so yes, so we're going to do some. We are going to do. That's what this is about. It's about transformations today, all right? And what we're trying to show is that we can do this using basic physics plus a little bit of geometry. Should we do equilibrium of forces in this case, or equilibrium of stresses in this case? If I'm going to do superposition, what would you choose? Yes.
Stresses.
Okay, so stresses.
My reasoning being that with stresses, I think it's easier to correlate the two stresses together between the two cases, one where it has like the two cases that you've drawn. I think that using trigonometric functions, you can relate the two. That's
Okay.
my reasoning.
Okay, yeah. That's okay. They're not acting in the same direction, right? And here's the kicker. Are they acting over the same areas? This is when it gets dicey. No, they are not. Okay, so now, why do you think 5 minutes or 10 minutes ago I drew these two diagrams? All right? Because we need to know what areas they're acting on, and we need to know something about direction and how they're acting on those faces. Okay? So this is when it gets fun. Okay, so, and this is when I'll probably make a mistake, and then you'll have to hopefully not get too upset with me. All right? I still like doing summation of forces in the horizontal and the lateral directions, or horizontal and vertical directions, all right? So often we're still interested in doing summation in the x Actually, let me use a different color. I'll use black. X and Y. Okay. So how do we go about summing things in these different directions? Okay. And I'm going to lie because we actually are going to think in terms of these x prime and y prime directions. Sorry about that. I like to think in terms of x and y, but sometimes we had to give it to the team. Okay? So let's first do the easy part. Well, maybe they're both easy. Okay? They just have to be done together. Let's call this, since it's on a very small thing, we're going to call this delta A. I need another color, green. Okay? So what is the area over here on this side of that face? Try again. Remember, this is theta on this side. Not, it's up here. Yeah. Okay. This is why we're doing this, because it's tricky. Okay. So now that you've done that one, I'll do the easy one. Thank you for helping me out. Okay. Everyone see that? Okay. So now we've got some areas that these things are working on. We're going to zoom in here. I want to get components that are in the x prime and y prime direction for this stress. Okay? So now, all right, what I'm going to do is I'm going to draw these components like this. Okay? You see that? Do you believe me that I can take this vector and break it up into two orthogonal components? Okay. Now, this one would be in the x prime direction. This one would be in the y prime direction. Okay. See, this is super exaggerated. I made everything exaggerated. So what component, what would I write here for this face? Or this side of the vector, sorry, not a face now. How much is in this direction, in the x prime? Yes. Sigma, say that again? Okay, that's going to be contributing to sigma x prime, I agree. That's correct. Okay, that's what we're going for here. All right. And what's this? The other one then will be, this side will be sigma x sine theta. And it's not good. Sorry, let me change this so you can actually probably see it. Okay, there you go. Okay. If I move to this component, all right, again, exaggerated triangles. I need one that's in the y prime direction, and I have one that's in the x prime direction. So this component, right, is going to be sigma y cosine. And this component is going to be sigma y sine theta. All right? So now we've got our stresses, all right, or our normal stresses in terms of the new coordinate system. We've got areas in terms of the new coordinate system. We haven't defined our taus in terms of the new coordinate system, okay? So we can have a stress component similarly like that, okay? To make our lives really fun and exciting, okay? So, let's have a little fun here, okay? Let's have a little fun. We're going to do some summations, okay, on these different faces to be able to perform equilibrium, all right? So if we look at equilibrium for the x direction, or the x prime direction, okay? We're going to do summation of the forces in the x prime direction. That has to equal to 0, right? So what do we do here? We have sigma x prime. Okay, so let's start with this one. What's the contribution of sigma x prime in the x prime direction in terms of a force?
Sigma x prime divided by delta A.
Okay, almost.
Or, right, yeah.
So sigma x prime times delta A. Okay. Does tau x prime y prime contribute anything in the x prime direction? Huh? No, it doesn't. Right, because it's orthogonal to it, right? It's in the y prime direction. So that's gone. We forget about that. Forget about it. Okay? Now, let's do the sigma x, because that's probably the easier one. Okay? So sigma x is acting on the delta A cosine theta face, right? And which of these is acting in the x prime direction? The sigma x cosine, right? And it's going in the minus this direction. So we're going to do minus, okay, times delta A cosine theta. Okay? Questions on that? This is if you understand this, we're on our home, we're on our way to winning the World Series or something. Okay? Questions? There has to be a question on this. Everyone, is this crystal clear? Yes, Kevin.
So when you set up the sum of the forces with respect to x prime, you are still relating the original stresses just with respect to the new direction? That's
Yes.
where the cosine and the sine come in.
Yes. And maybe, I'm glad you asked that, Kevin, because what is our goal? Our goal is actually to figure out what sigma x prime is and what tau x prime y prime is, okay, in this particular configuration. Notice I didn't say our goal is to figure out what sigma y prime is with this cut. Why? Because there's no sigma y prime drawn here in this particular cut. I have no face on which sigma y prime is acting through or coming out of, okay, with this particular cut. I had to do another cut, which we'll show you, okay? So this is the component, the contribution of sigma x in the x prime direction, sigma x cosine theta, acting on the appropriate area, delta A cosine theta. Okay? Now, let's look at tau xy. Tau xy, you guys tell me, is tau xy, first of all, is tau xy this one on the left side, not this one down here, but this one on the left side, is that contributing in the positive x prime or in the minus x prime direction? Good. Okay, and what is its component in that direction in terms of the stress component? How would you describe that?
Tau xy sine theta.
Good. All right. And on which face? Excellent. Okay. Moving on. Let's do sigma y first. All right. What is sigma y's contribution in the x prime direction? Well, you have to decide whether it's negative or not. So remember, we follow the arrows. We're coming down, and then we're going to the left. Okay, coming down, going to the left. So it's going to be a minus. And this is that little component right there, right? That's the sine. And it's acting on the delta A sine theta area, okay? And there's one more. Tau xy comes back to haunt us again, okay? And this time I didn't draw the components, okay? But you tell me, just by looking at it, which direction is it contributing? Is it contributing in the positive x prime direction or the negative x prime direction? Negative. And by what amount?
Cosine.
And on the anything else? I think we're done. That's it. Okay. So when you do these out, what you get is a bunch of terms times delta A. Delta A then goes bye-bye, right? So we can put x's through all these deltas A. Okay. And what we will get here, if we do this somewhat carefully, is that is going to be equal to sigma x cosine squared theta. And we're going to have a, in this case, we're going to have sigma y sine squared theta. And we will have a tau xy cosine theta plus sine theta. Man. Just like that. Okay? And then you'll see that we can do some, yes. Did I do two? Would I do two tau? Oh, yeah. Thank you. This is why when you run on Scratch, you sometimes make mistakes. Good. Okay, good. Okay, so then you can do some trigonometry, okay, as done in the slides or in Hibbler's book, all right, and you can get simplified expressions here. We did a lot of stuff with variables, okay, and how do I put this? Ultimately, how do I put this? You're going to end up using a lot of numbers in this part of the class, okay? Because, one, if you're doing the free body diagrams, like if I ask you, like you'll see exam, I think both the summer exam and the spring exam asked for you to do it using this free body diagram based technique for one of the problems. Okay. And we'll learn in a little while, we'll learn about another technique which is more circle, which is also using a lot of numbers. Okay, so this is like a strange part of the class where you're going to be plugging in a lot of numbers, and often it makes sense to work in terms of numbers instead of variables. Okay? But there are, as you can see here, there are variable-based expressions that you can use, okay? And they're in the notes. To get started though, please just try to use only the components that you need to use. Do you see that this was a little bit overkill? If I had no tau, if in the first problem that we looked at here, okay, we only had sigma x. We didn't have a tau xy. Okay, we didn't have a sigma y. So if you were to do the free body diagram, right, with the numbers, you wouldn't have even drawn sigma y. You wouldn't have drawn tau xy. Right? And then you would only be looking at what are the contributions of sigma x and how do they influence sigma x prime. Okay? Any questions? Any questions? Okay. Yes, Daniel. Yes.
Can we solve the problem using this free body diagram?
Okay.
Given problems from the previous sessions, I just learned a lot.
Okay. Well, let's see here. You tell me, which example do you want? 17.1, 17.2, question 1, question 2, 17.2. Okay. You sure you don't want me to do the homework problem? Okay. Oh, 17.2. Okay. So example 17.2, which you can find in the videos. Yes.
That's why you say that that's not a question from the homework?
I'm saying, I offered example 17.1, example 17.2, question 1 or question 2.
Question 2.
Question.
Question 2 of what? Oh, which one?
Session 17.
Okay, 17. Okay.
All right. So which one are we doing? We're doing.
One from the homework.
Two.
Question 2 from the homework. That's it.
Is that more amenable to what people want?
Two, yeah.
Okay.
Professor,
Yes.
is it 17 or 16?
17.
Okay, thank you.
And the secret is 42. All right. So here what we have is an element where we have
Professor, what is the shape of the equation?
what do you mean, what is the shape?
Do we have the shape or we're not given shape?
No. So today, okay, good, Daniel. Today and everybody, the point is that you've got some big geometry, whatever it is, a beam, right? You just spent last homework figuring out how to work with different loads contributing to different types of stresses, right?
But that
So-
doesn't answer my question.
So this could be some type of shape, all right? It could be some type of shape.
But then it doesn't answer my question.
The shape is not important. The shape of the body is not important. This is a square. Okay, this is a material element where you're given the state of stress, and then you're expected to be able to figure out what the new state of stress is just by rotating the element at that location. Right? We said at the beginning, we have an E, and we have rotated some amount, okay? So we have a sigma x, let's say, of 75. We have a sigma y of 100. Okay, and we do have tau xy. And this is going to be, for our purposes, 25. Okay?
And this is our theta.
These are, yes. Okay? Now, here we have some options, okay? Let's just say that we're going to take a slice and that slice, I'm really bad at drawing lines, as you know, okay, is 70 degrees. Okay, I'm trying to make it exaggerated. So I'm trying to make it closer to 90 degrees. Okay? So this is what happens. Sometimes you're like, okay, I'm interested in what's coming out. All right, what I'm interested in is what's coming out of this face. Okay, this is going to be my new x prime direction. Okay, and I want to figure out what sigma x prime is. Okay, so what is So it's important to be able to relate this. This will become key later on too, to what we just defined in our convention. So this angle right here is 70, right? That's a 70. Do you remember where how we defined theta though in the previous case? Theta, remember, look, the angle of rotation is this theta. But that theta then ends up being equal to this small angle in the top left. Okay? So, if I'm really trying to keep my convention correct, this is going to be theta. So, given what you see here, what is theta equal to in numbers? Yeah, it's equal to 20 degrees, right? Okay. So it's equal to 20 degrees, and I've got my sigma x prime coming out of here. I have a tau x prime this way. Okay. I had in the past my tau xy and my sigma x like that. Okay. So I've now got to do the equilibrium. Okay. So let's do it. This we're going to call delta A, right? What is this one over here? The vertical one. Yep. And this one down here is, okay? So you tell me, what do I do next? Or how would you do it next, based on what we discussed? Yeah, so let's start thinking about the forces and the contributions, right? So we're going to say that we're going to sum the forces. We're doing equilibrium on forces. if I got that, then I'll do sigma x prime A, delta A. Okay. Now, which one do you want to do first? Let's do the sigma x first. Okay? So sigma x is 75 megapascals, and it's positive 75 megapascals, so it's going to be minus. Okay, times what? If I think in terms of a distorted triangle, is it going to be cosine theta, sine theta? What am I going to use for the force component? The direction of the stress. Well, we remember, so x prime is in this direction, right? So now the component of this sigma x that's acting in the x prime direction is that one, right? And that's in the opposite direction of x prime. So it's negative.
So X prime is the positive direction.
Mhm. Yeah, because we're doing equilibrium of forces, right? We're summing the forces, and I already said sigma x prime delta A, and I'm saying it's minus 75 megapascals, and I'm saying which component? So it's going to be the cosine component, right? And then it's going to be acting on the delta A sine theta face. Right? And we said earlier that that's fine. We can even put in the numbers if you want right now. Like that. Okay? We come over here, we have a tau xy. Okay? Tau xy was 25 megapascals, and it's positive, at least by our conventions. So if I'm thinking about the component that's acting in the x prime direction, is it positive or negative?
Which one? So
Tau xy, this vertical tau xy.
negative.
Correct. And what is the quantity? Or what is it times? What component of it is it?
Tau times.
So in this case, it may be helpful to draw it out again. And it's distorted, right? So this is theta. Huh? I would say sine, actually. Because it's this component. It's this bottom component.
Oh, we want the bottom.
It's this component that's going against the x prime direction.
I thought we were saying the minus.
Yeah, so it's going to be, so we're going to have a minus tau xy sine of 20 degrees, okay? And it's acting again on the delta A cosine face, or delta A sine face. Okay? Down we go to sigma y. Is sigma y contributing positive or negative? Well, sigma y was 100 megapascals, right? So 100 megapascals, if I break it into its components, it's going to be contributing. I can go this side this time. Okay? Whoops, that's not right. Boom, 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 boom. I won't go that way. I'll go this way. Right? That's contributing again in the opposite direction of x prime, so it's going to be minus. And is that a cosine or a sine? It's going to be a sine. Okay? On the delta A cosine face. Okay? And then there's one more, the tau xy. All right? And in this case, what am I interested in? I'm interested in a component that does this. That's gonna give me a cosine on this side, okay? That lines up with that. And it's minus tau xy cosine of 20 degrees on the delta A cosine face. And this all equals 0. Okay? So this means that, and then I cancel out all the delta A's, so this means that sigma x prime is going to equal 75 megapascals times cosine 20 degrees times sine 20 degrees plus tau xy was 25 okay, plus 100 megapascals, that's a sigma y, times sine of 20 degrees times cosine of 20 degrees, okay, plus the 25 megapascals times the cosine of 20 degrees times the cosine of 20 degrees. Okay? And that quantity is 94 megapascals. Okay. Any questions? All right. What's that? All right. Good. So, on the homework, you're going to have an opportunity to explore doing this geometrically. You'll then be able to use a set of equations that describe the transformations. And then finally, you'll get to use some tensor math. Okay? So for that, what you'll see is that we can use a couple of matrices, the rotation matrix times the stress tensor times the transpose of the rotation matrix, okay, we'll be able to tell you what the state of stress is. Okay. And I highly suggest that you take a look at using the Colab provided. I'll just pull that up for you. So if you go to the notes section for session 17, you'll see that there is a plane stress 1 Colab. Okay. And I've timed out, but you'll see that there's the example 1, example 2, example 3, and you can use those codes if you like to help do the other things. Now, one note, there's going to be a problem where it says, hey, what is the angle rotation necessary to get something to be equal to 0? Okay? It's not a bad idea to plot that out on Colab and then see where it crosses 0. All right. I'll be going around to answer questions. Yes, Jay.
I think it'll be easier if I just show you.
Yeah. Okay.
So would I be wrong in thinking that because sigma x and tau x are parallel, you can just kind of shortcut it and say if the x direction, x prime direction, sigma x cosine theta is this, you can just kind of substitute it and just do something like that. Because they're parallel, the angle should be the same.
Yeah, as long as you make sure you keep the areas right. I mean,
Yeah.
you
It's
can
just
get-
for the components themselves.
Yeah. That's okay. That's okay. Just make sure you keep it straight.
Yeah.
All right, keep it straight. In the end, we will end up using different techniques. Oh, really? No one told me. Thank you. Hold on, let me take a look. Oh, yeah, thank you. So, thank you for, next time, just point out the error. You did a great job. Thank you for pointing out my mistake. So, if you didn't catch that, I made a switcheroo, but it's correct now. The answer is the same, yes. Okay, other question? Yes.
Yeah. For 17 years. Part of the effort. Yep.
Okay.
I'm gonna try my best to do it.
Okay. So there's a question about number 1. Okay. So we have ourselves a cylindrical pressure vessel. Okay? And a cylindrical pressure vessel has a longitudinal direction and a hoop direction, right? So in this case, we'll call that one sigma x, and we'll call this one sigma y. Okay? Did you have a question about this? Did we agree up to this point? Okay. So, what are sigma x and what are sigma y here? Yeah, and so in terms of quantities, and good. So sigma x, sigma y is going to be PR over T. Sigma x is going to be half that, right? Okay? So what I'm asking you to do is take that element
Didn't say that TXY is TX plus 2.
like that. And then we're going to rotate it 45 degrees. Okay? Okay? So you have to do the calculations for the new state of stress. Right? You're going to have a sigma x prime, a sigma y prime, okay? And you can be interested in the shear stress, right? Okay? Is that enough to get you going?
Okay, so should we not like this surface?
Yeah, it's the same location, but all we've done is rotate the element. That's what we've been doing. The shear is going to come from equilibrium, right? When you do this cut, and what I highly suggest when you do this cut, is even though it says 45 degrees, make it exaggerated. Okay? So the shear stress that you're going to be interested in is tau x prime y prime. Okay? Right? And you had no shear stress. So now you have a sigma y and you have a sigma x. Yeah, there's going to be a tau x prime y prime. Because we rotated, right? What there's in this configuration, right? The sigma x prime can take some of the both of these components, but the tau x prime y prime also takes and absorbs some of this. That's right. Okay? Very good. Very good. Your name again is? Okay. Good. Okay. So let's let folks get their attendance taken care of. And I'm wondering how you all are. You've done all these problems already. This is really good because I see lots of people ready to go. So, yeah, we're here to try to give some assistance. Okay. So I just gotta say that this stuff that we covered today is absolutely critical for exam number 2 and the rest of the class. Right? Just take a look at the previous exams. Look at the final exam. You have to be able to do these transformations. All right? You have to be able to do this. Yes. But leave it like that. Hold on. Please also though make sure you take the attendance. All right? Get that.
So you're getting ahead. You're getting ahead.
Is there a problem? Oh, okay. I have no idea. We're still in class, so don't shut the lights off if you can.
Yeah, no, I'm
We
seeing,
got-
I saw it, but
Yeah. We got a few more minutes.
it's like, it's sending me down here, seasonal.
I'm missing.
Thank you, Jane. Yeah, the checks
We've gone through and we explained how we get about X, this matrix, orientation about C is this, this line is this. When you're doing the 2D transformations, when you have X and Y, which axis is this? That's right, okay? Which axis are we rotating about?
Okay, so we're rotating, that's what the question says, rotate 90 degrees about the positive rotating axis.
So we're not using this matrix. Alright, so when you look at the or if you do your decimals, whatever you want to do. That's fine. This is the
I just know when he said 11, he meant to call that for what?
yeah. So not what it is
But like, you find a good score. Fuck you. How do you find I guess it's more confused on the math. Or just the math around the
Yes.
Yeah. How do we know what the value is going
Good question. Okay. This is our X under theta.
Yes.
So if it's a positive, it's like everything, right? Theta. Yeah, so there, and then that theta equals to 20, and then goes here.
I'm drifting on this.
What? These are the values that are specified. In this case, it's
So if I get 90 from theta,
yes.
and then I change the cross product or something, so it's 1 and 2 plus this.
R, that's the rotation matrix, times the stress tensor, times the transpose.
It's
Oh, yeah, so this is easy.
Last name that is absent, it's a complication.
That's
And I prefer that I think it's my
I actually just wanted to.
Actually, no, that's like it's over.
Oh.
Bye bye do series.
Right, so I think going back, I mean, I make mistakes on this too, right? But at the very beginning, I was trying to show that we all learned many moons ago, right? That we have two components, the cosine and the sine, right? So what I find very helpful is to always make these things exaggerated, all right? So I didn't do it here, that's not always, right? But what you do when you're drawing these vectors out, let's just say it's in this direction, okay? And actually, no. Let's say it's in this direction, but I know that the x prime is in that direction, right? So what I've got to do is I've got to figure out how to draw this vector that in a way that gets both one of the components in this direction.
So just like figure out like how the triangle's supposed to look like.
Yeah, so exactly. So like this triangle has got to look, so I'm going to draw one like that.
Yeah,
I'm
'cause
going to
that's
draw
the
like
match
that.
with the-
Exactly. And this is the smaller angle here. Typically I'm trying to make it exaggerated, and that's a small angle. So then I know that this component is in the same, it's parallel to my x prime direction.
Okay, so,
All right.
so that means, yeah, in that case we'd use cosine.
Correct.
But for shear, it would just be like, if the sigma is this way, we just draw a line parallel to the shear stress, and then connect it with some random line. Right?
Yeah, so shear stress is a little bit different, but it's, I mean, the same principles apply, right? I need to break these up, okay? I need to break this vertical component up into two components where one of them is parallel to the one I'm interested in. Okay, x prime. So, look, that's what I did here. I broke it up like that, so that this component, right here is parallel to here. And again, I'm using the smaller theta, right? The small theta, because I made everything exaggerated. So theta here is going to be here, so this is going to be sine. This side is going to be sine. Okay.
The issue with like that I'm having is when I draw the triangle, it does not look like a 20-degree like, angle. It looks more like
45?
Yeah.
Yeah, so that takes a little bit of practice. You always want to make it exaggerated. Okay, I didn't, like, so like here, right, I didn't make it exaggerated. I probably should have, right? So like, you know, really acute when you make these. Okay? Yes? Okay, so, okay, yeah, so, I haven't gotten to a lot of that stuff, so I'm gonna catch up. I'm okay. Yeah, as long as you publish your stuff, you'll be fine. Okay, it's there. If it's not there, just send me a message and I'll get your for next week. Okay? Great, thanks for letting me know. Yes?
So, I see a pattern. I don't know if that's so we're doing this for like static, just finding the stress on static. But are we gonna have to find a different? Are we gonna have to? Right now, the rigid wall pressure level is static and it's not twisted, are we gonna have to find twist it and then?
Well, so, yeah, there is still all statics, right? We're all
Both are like static, right?
Both are statics, but yes, we spent the last session talking about combined loading, right?
Oh, okay, it's fine.
Exactly. Right? Exactly.
Good stuff, good stuff.
Okay, so it's really helpful to get this aspect down. This is one of the key things that we can mechanics. Good, Andy, see ya. Bye-bye, see ya, Michael. So in this case, it's asking for the maximum in plane shear, right? So that's what you were getting at.
The same process until I got to and then
Yeah, let me go ahead and shut this off. Since we're past the time. Hold on. Okay, everybody,